So I'm going to present you a project that is actually funded by the IMF and by Raphael here. And the starting point of this project is to realize that some algorithms to solve the SGE models are quite well established. So maybe it's time to lower the barrier, the entry cost, and make them more easy to use, to implement. So part of the project includes constructing a software that is as easy to use as possible for the end users. What I mean by that is we want to have a way to write the model in a text file, to import the model, check the model. This is the RBC, so there are some glitches, excuse them. Check the steady state, and then, is it going to, for everyone? Then, here we solve the model at first order. We get the perturbation, which is a kind of extrapolation using a single point. And then we solve the global solution. So by default, it's using a Smolyak polynomial, the collocation version. So of course, then it's only simple programming to provide some function to plot, to simulate the model. Oh, that's a big problem. So the goals for this project is to find a way to write the model in a text file that is completely independent from the solution algorithm that will be used and independent from the software, so that models can be exchanged between people who use different software. Then another goal is to provide with a generic solution that work well with generic models. And one important part is to do it as efficiently as possible. So as we have already discussed a bit today, efficient is a bit subjective. It depends who says it. Everyone does efficient code. For instance, the Smolyak collocation version, it was 40 milliseconds to solve the model. But is that big or not? It really depends on the scale. Actually, there are 20 points, so it's not very impressive. We also want, because part of it will require some low-level code, so we want to write once for all this low-level code for instance, interpolation, solution of sparse systems, that kind of things, and make them available for anybody with a free license. But in this talk, I will consider whether it's possible to actually not use low-level code and use Python. And I will argue that in some sense, this old gap that there was between compiled language like C, Fortran, and so on, and interpreted language, this frontier is completely blurred. It's much more complex now. So I will try to explain that. Sorry, so maybe I'll skip here. So today, I'm not presenting the software anymore, but I will just show you how we standardize the model, how we write them. It's interesting because if you have written the models in a standard way, then you can compile the model and produce, for instance, MATLAB code with symbolic derivatives. We can produce Fortran code, C code with the same model. So then we can check various solution algorithms. That's one thing. Then I will talk about the compilation, how you compile the model so that it's actually as fast as possible. And finally, I will compare a bit CPU versus GPU implementation. So there will be a bit of overlap with the talk by
You use the word
Eric.
compile, but then you just apply it to the model. But
Sorry?
You say compile
Yes.
the model. But
I use it.
to compile the solution code.
Yes. Actually, I use compile at several, in several sense. It's always when you have some high-level code, you translate it in lower-level code.
Well, machine code.
And then machine code is one example. But there are many, many steps in the compilation process. There are already many steps. For instance, if you use GCC, you have the C code, and the C code is compiled into an internal representation. There are several internal representations in GCC before it's compiled to machine code.
Yeah, I never thought about looking at anything in between.
No, but I mean, some people call compilation producing machine code. I use it in a bit more general term. So I will say I compile the model, but then I will also talk how I produce actually machine code. Yeah. I have a big problem with it.
It's just because of...
Okay.
All right, thank you.
So we just stay there maybe. So the rationale for model standardization, well, it's always a new standard. It's just a proposal, okay? You do whatever you want with it. But the thing is that there are a few ways to write models for perturbation software. There is at least one piece of software that solves global models with smaller collocation, actually, GBench, and there is a toolbox in MATLAB with various routines, including generic routines, but they don't offer you a way to write your model. They tell you how you must write your MATLAB code, so it's more an API. So the advantage, I already talked about it. So it's completely open technology. So we use this YAML format, which is serialization format. Serialization means it's pure content and it's independent from whatever you want to do with it. It's very easy to parse. You don't have to implement a new parser each time.
Is it stand or something? YAML?
So it's yet another markup language. But that's not my invention. I decline.
So
But
how general purpose is it? I mean, suppose you wanted to adapt it to I don't know what it looks like, but to like the microeconomic kinds of models with many different agents or something. But one of the weaknesses of Dynar is, and what you've said so far is, you need a representative agent, steady state kind of solution.
Yeah.
So if we wanted to represent a population that is evolving over time.
I think for population, you have to. I haven't proposed anything for that, but it's possible. You can do that. YAML is like XML. You can put any piece of information in it. So. That's a disaster. So everything. So for instance, here is what I call an FGA model, but it's simply the model consists in a stochastic process. The stochastic process gives you the evolution of the states between t-1 and st, and t as a function of innovations. And it's controlled because you can actually choose the control x. And there are also the controls x. You choose them so that some optimality conditions are met. And you also have restrictions on the set where you have when you can put your controls. So actually B bar, both B can depend on the state. So here we use this shortcut that we can define auxiliary variables, but basically they are replaced everywhere.
By the way, the upside down T, do you mean for it to mean complementarity as in the complementarity literature?
Yes, exactly. That's
Because that doesn't look like how it's normally written anyway. So
what?
that doesn't.
How would you write it? I mean the perpendicular.
Anyway,
It means that this, for those who are not, so this has to be true, but this is not true, then it means that you are on the upper bar. Sorry, if it's positive, you are on the upper bar. If it's negative, you are on the lower bar. So it's always, you have to remember which side it is, but basically that's it. So this is sometimes equivalent to the value function, because the value here will be the Lagrangian, and the Lagrangian associated to each control, they are either positive and no, they are either 0, you are not constrained, or they are positive, you are constrained on one side, negative, constrained on the other side. It's actually more general than value function. Because, for instance, if you have a model where you have two agents who maximize their values, and you want to look at the equilibrium market, then you can code it that way. It's not clear how you do if you have two people maximizing the...
There's no constraint on where S lives.
Yes, there are. There are. So in the file corresponding to that simple model, this one, so basically you say which are the states, the controls, auxiliary variables, you give a set of parameters. So this is the declarations block. So you define symbols. Then you use symbols to define equations. These equations are ordered by some groups, and at the end you can give some values for the parameters and also the variables. So this either means a steady state or an initial value. So actually everything is solved as a single system. So you can have parameters that depend on steady state variables and vice versa.
Can you impose constraint hierarchy simple bounds?
You can, but then it's your call to make the algorithm. I mean, the file is quite flexible in its own. What I'm not providing is an algorithm to solve any kind of model. I don't even intend to do so, or to try. Because the nice part is it's actually, what did I do? For any model, you have this generic structure, declaration, equations, and calibration. And you can define your own type of model in what I call a recipe file. So for the FGA model that we have just seen, the recipe file defines what is to be expected in your model. So I say my model has to contain states, controls, auxiliary. There are 3 types of equations, and for instance, the arbitrage equations, they contain states at date 0, at date t, controls auxiliary at date t, and other variables at date t+1. So using that simple syntax, you can also define, so there is a non-latexification, so you can define a model where you have explicit expectation. So if you read the LaTeX, you see that you give the function g for the transition, the arbitrage for function f, but then arbitrage is a direct function of expectations, and expectations are defined in the separate equations. Or you can also, define, I think I'm disconnected from internet. You can define value function problems. So here you have the evolution of states and the value that you try to maximize. The nice thing is that for any kind of this model, you will have the same infrastructure to compile the model, differentiate, produce the output, and then you do what you have to do. Okay, so you can also write Diner model where you make no difference between states, controls, and you just put all the variables in the model and use for all the equations. So this is very flexible. For instance, there are 2 papers that I've been working on where we basically take this FGA model, which is a basic time iteration model, and we add endogenous distribution of shocks. So we just define how another type of equation for the distribution, and we implement the solution. Or in this open economy paper, what we have is discrete Markov state. So we specify transition matrix, and but we use the same ingredients, the same compiler, the same approximation routines, and so on. Is that? Can I have? Sometimes it works, sometimes it doesn't. I don't know. So I will. I will now consider. I'm sorry, but. So this is a simple solution algorithm for an FG model where you have G transition functions, F the arbitrage equations. So here, the things to notice is that the algorithm is vectorized, meaning that, I mean, you're all familiar with it, but we have a grid of points. It's a two-dimensional object, and we are looking for the controls on this grid. When we know the controls on this discrete set of points, we can interpolate and we construct a smooth function. So given a guess for the controls, we can compute the transitions tomorrow. There we have the states tomorrow, and then we want the controls tomorrow, so we have to interpolate. And when we know the state today, the controls today, the states tomorrow, and the controls tomorrow, we can compute the residuals for one realization of the shocks. Then we integrate these shocks using some quadrature. And we iterate these steps using a nonlinear solver, and we iterate until the difference between the solution at two different steps is smaller than some criterion. So what we need to implement that we need to be able, but we need to implement it efficiently. Yep.
So the unknowns are the function values at that grid point.
Yes.
So it's going to be a big system.
So what?
Okay,
It's a big system, but the matrix is sparse. Because you could solve for the points separately, okay? If you solve for them all at the same time, you will compute the Jacobian, but you know that the Jacobian is sparse because each point is independent. So you construct this big Jacobian. But then the payoff is that every time you evaluate function f, you do it at full speed because you're operating on big vectors. And what I will explain in the rest of the presentation is that basically these speedoffs are very big. And they are typically overlooked if you make a simple parallel algorithm for each point. Okay. So I have some remarks about this algorithm. So as I said, the vectorized algorithm has some payoffs, it has some costs. The costs are that you are not solving for the points independently. You solve for the whole grid. So imagine that one initial guess is already near optimal, and another one is very bad. You will iterate, and you will over-optimize this point that was already an initial guess. So you will do 5 iteration steps for all the points instead of doing them only for the bad part of the state. Okay? But that's a cost that we accept. Another problem is that if you operate on each point separately, then the kernel or the simple processing unit that you assign to each point is operating on a small data set. Actually, it's not that simple. Each kernel does small calculations, but it has to share a big amount of memory with the other kernels, right? This big amount of memory is the guess for, is the former guess for the controls tomorrow. So that's a problem that you have to solve for any parallel algorithm, how you distribute this common information between all these small workers or kernels or tasks. Okay? So in that respect, I'm not sure that this kind of recursive problem, also value function iteration, can be considered as embarrassingly parallel. Because embarrassingly parallel is you have many tasks to do, and you don't have to care about how you make the parallelism work. You just distribute it. But here you have to think about the data. Okay, so now the question, I'm separating the efficiency question. One question, how do you make this model evaluation fast and as fast as possible? So there are many ideas. Actually, part of them are automatically done in your compiler. One idea is to apply symbolic optimization on your expressions. For instance, if your expression computes 2 times the same term, for instance, k power theta times z, and you have it in 2 different places in your expression, then you can detect it, and you compute it only once. Okay, so one option is to go for low-level programming, but I will argue that it's not. There's a bit of voodoo in this approach, and it's not clear that it always works. And then you know that the hardware, you try to use it at its maximum capacity or velocity. So you have the vectorized expressions, vectorized instructions that are in the processor. You have the multi-core structure of the processors, and you also have the GPU that you can use for that. So now we'll talk about this difference between interpreted and compiled languages. So there is this simple idea. So here you have a loop expressed in C and the same one expressed in Python, which is the interpreted language that is represented today. So in C, you express this loop. You have to type all the variables. And if you compile it, even for n relatively small, you will see that the Python version is at least 1,000 times slower or even worse. So it's not an option to write code that way in an interpreted language. Then, if you have looked for workaround while, for instance, writing MATLAB, you have tried to optimize MATLAB code, and you came to the conclusion that no matter what you do, it's always slower than a compiled language. Actually, it's worse than that. If you spend some afternoon writing the code in this compiled language without any special optimization, it's faster than what you had in your interpreted language. So that's this informal conjecture that you can never beat naive C or Fortran code. Actually, the situation is a bit different between C and Fortran, but I focus on C, I know it better. So there is a reformulation that is a bit more honest for this informal lemma. Actually, what is really efficient is automatically optimized C code, because you apply this optimization from the compiler without knowing it or knowing it, but this is what really makes the difference. Well, it doesn't explain why interpreted languages are slow.
Fortran on purpose?
Sorry?
Did you drop Fortran on purpose there? Or?
No, the thing is Fortran has some strengths that C doesn't have. Just to evaluate it now, it has more high-level information about the code. For instance, it has types for arrays. It understands arrays natively, so it can perform optimization on array operations. I don't exactly know if it does it or not, but I'm sure that C cannot do that kind of thing. I mean, there is a reason why Fortran is very popular for scientific computation. So now this question, why are interpreted languages so slow, actually? The reason is that most of the time, these interpreted languages also have high-level features. They are object-oriented, for instance. And what they do is they tend, even the smallest integer is inside an object that has methods, properties, and it takes time to create this object. So when you store the integer in the memory, you also create this object, and there is a big overhead for that. And when you add two integers, what does Python do? It says, OK, so here you want to do an addition. Then, oh, that's an int. I check that it's an integer. And this could be anything else, actually. So, oh, it's an integer too. I add them together. And so it's checking the type at all single operation. And that's extremely slow. So you can also work around this limitation. It's basically what MATLAB does. Not a single one. So this is MATLAB code, except it's written in Python. So you say, but the logic is exactly the same. You say, OK, I will define a function that operates on two arrays, A, B, and C. These arrays, what they do is they represent big, often contiguous parts of the memory. And when you perform the operation on these objects, what you do is asking some low-level library of your computer to perform this operation. So, for instance, if you do matrix multiplication in MATLAB, you are calling the MKL libraries written by Intel, which are very efficient, and you cannot beat that. So you are, for these 2x2 operations, you are extremely efficient. But it's not so efficient. Why? Because for this simple expression, how does the interpreted language do the thing? It checks, OK, so it looks at the code tree, and it says that it has to perform this operation A times B. So, OK, sends it to BLAS, get the result in some other part of the memory. So there's a creation of one temporary variable in the memory. And then it adds 1, and it creates another temporary array. And it multiplies it by B, and it gets the result. So you have, well, at most, created two temporary arrays that you don't really need. And you have been writing in the memory. And as I will explain later, that's the main bottleneck of your computer, the memory, not the processor. OK, so this approach is slow when the expressions become complicated. There is one known solution for that problem too. It's called lazy evaluation. So basically, the compiler encapsulates these matrices in some objects. And when you perform A times B plus 1 times B, it creates the abstract syntax tree. And then when you want the result, it says, OK, what's the most efficient way to compute that? It computes that, and it gives you the result. But it doesn't create all the temporary arrays. So there are some libraries to do that. It's also, so there is the Python Cyano library that does exactly that. It's also possible with compiled code. For instance, I think the thrust library is a template library. So if tell me if I'm wrong, but I think if you write that thing in thrust, it will produce an abstract object, which is actually a template. And at compile time, it will translate this abstract object in a series of instructions that have been optimized. So it's optimizing all these kind of operations. Oh, but of course, it's a problem that you can do only at compile time. Okay, so there have been two game changers in the computing landscape. I mean, at least in my computing landscape. So the first one is these families of just-in-time compilers. The second one is the low-level virtual machine. I don't know if you have ever heard about this one, but so what are just-in-time compilers? If you have this function written in Python, so I said, if you write it that way, it will be slow because it has to check for the types at each single node. Okay, but if the language knows the types of A, B, and C, then it doesn't require so much intelligence to deduce that I, given that I is clearly an integer here, that will be a float, that will be a float too. So it can deduce the types of these operations. And what could this clever interpreter do? It could write C code, compile it, and execute it. So that means that it can create a code exactly equivalent to C code for simple snippets like that. Okay? So that's exactly what the Numba library is doing. They have a just-in-time compiler. You put it in front of the function. First time the function is called, it's compiled for the given arguments, and you get something that executes at machine speed.
So where did you specify the types?
It's the first time you call the function. You call the function with some arrays, one array of doubles, one array of double, one array of integers, and it says, okay, so I will type this function with these types, compile it, and the next time you call it, I will use the compiled version. You can also compile it ahead of time. So actually, Numba, it's funded by the DARPA. They have a lot of funding, and they are the official solution for Python and CUDA. They have been endorsed as the official language for the official Python for CUDA. Okay, so and there is also this Julia language that you should at least hear one. It's a language that is really similar to MATLAB, but it's designed so that just-in-time compilation is as efficient as possible. So when you write Julia code, you always have something that's close to machine performance, even if it's a high-level language. Okay, so LLVM, I jump here. So I said in this short discussion that the compiler has an internal representation. It has many of them, actually. And some guys have said, okay, if we can standardize this intermediary representation, and we can perform optimization on this intermediary representation, then this can be shared by all the compilers. So it's easy to write. You take a given language, you compile it to the LLVM intermediary representation, and then you get for free the backends that have been implemented actually by the manufacturers. So there is an example. I said Numba compiles Python. Actually, it compiles it to LLVM. And then you can compile it to the processor. But there is also, this is why I say that the landscape was a bit more complicated than before. If you look at an NVIDIA device, the NVIDIA device has a just-in-time compiler. And the just-in-time compiler accepts PTX code, which is a kind of assembly special for the device. Okay? So the NVIDIA guys have written the translator from LLVM to PTX. And now, almost for free, we are able to compile Python code to LLVM and to the GPU. So it's relatively easy for Python library to compile GPU code. Okay, so just to be short, I said when you write C code, it's very fast. It's very fast because it's doing vectorization of your code. So if you write a flat loop, the compiler will say, oh, actually it's not flat, you are doing vector operations, which is a kind of a paradox, no? What it's not so good at detecting automatically is what data you want to operate on. Is it a very big array that you want to iterate on? Is it a two-dimensional array? The compiler doesn't really know because it cannot. So it will not be very good at dispatching the data where it needs to be processed. So when you have multi-cores, you can write code that is more efficient than C code. Okay, so I wanted to say there is a basic fact. So it has been observed quite early, like 95 by McKee. And the thing is, processor speed and memory speed, they both grow exponentially, okay? But they don't have the same coefficient in the exponential. And the result of that is that now memory speed is much slower than processor speed in relative terms. Like you see processor speed was at 1 in 1990, it has been multiplied by 100 in 10 years, while memory speed has been multiplied by 3, roughly. Okay? So the problem, and this is when you create the expression, the memory wall, or the starving processor. The processor is ready, but it doesn't get enough data. It's waiting for the memory. So what they have done is complexify the design of CPU. So they have added some small chipsets of memory. And since they are small, they don't have so much energy dissipation, so they can be faster. And then they have added cores with also many small parts of memory. What I really mean is that now the architecture is quite complex. So I'm not arguing that you should manage it yourself and copy data from the RAM into one of the cache, but you should allow the compiler to do it, and you should simplify its task. And that is easier actually if you do vectorized operations, like in MATLAB. You add 2 arrays, except that you have an intelligent compiler that is able to dispatch the calculation efficiently. So the best library for that is called NumExp. And if you use this library, what happened? So if you use this library and you compare C code, so you compare the MATLAB version. MATLAB really has a similar performance. You see that you cannot. What I'm doing here is taking the arbitrage condition of the RBC model and feeding it with a big number of variables. So if I have one, I go from 10 points to 1 million, 10 million. And so you see that at some point, the special compiled version becomes faster than C optimized by Intel processor. And actually the scale here, the difference is roughly E, it's a bit smaller than E, meaning that the C code is actually 2 times slower than the optimized version. And this was on my laptop actually. So we can do the same for GPU. Oh, one thing I wanted to mention. Oh, yes. So we can now compare the GPU with the CPU. The GPU is actually on the same laptop here. It's quite a small one. But you see that when the number of points we evaluate increases, so these are absolute times in milliseconds. This is 3,000 points and 1 million points. So clearly, for processing the data, the GPU is faster. The problem is when you load the data from the main memory, the RAM of your computer, to the global memory in the device, it takes some time here. It also takes some time when you want to retrieve the result. So your computation will be efficient if you can keep all the data in the card. Then there are these points. What are they? I said efficient is something subjective. Not so much, actually. You have some bounds on how fast you can go. And the bounds, they come from the memory. You know the memory bandwidth for this machine, it's 6 gigabytes per second. So it cannot fit the processor with more than 6 gigabytes per second. If you take the number of points and you divide it by the, you multiply, I don't know. I'm just a bit lost. But you can compute the theoretical maximum amount of information that you can compute if the processor is able to process the data at 6 gigabytes per second. So here you have the interpolation routine. Here it's a simple, I think, two-dimensional multilinear interpolation. And here it's a model evaluation. And in that case, you see that by optimizing the code, by compiling the model efficiently, we are extremely close to the theoretical bound. Meaning that here we are, in practice, we are memory bound. The processor is waiting for more data. And we will not gain, you can add 10 cores if you want, it won't change unless you put faster main memory. Here there is a bit more. So the problem is this kind of bound is a bit harder to get for the GPU. Because for the GPU, what you have is a transfer rate between GPU and main memory. And it's not clear that it's what you want to use, because if the data stays on the GPU, then it's not a good bandwidth measure. Okay, I will just go to the last slide. If I can just see what's. So I will just finish by giving you, okay. So you have the, I told you in the beginning, you can enter a model in a very naive way. Now we can compile them efficiently, and we can implement the time iteration method, because all the steps, they're actually quite friendly with the GPU, like the model evaluation, even the inversion of the matrix. If you hand code the inversion of all the small matrices, then this inversion can be done in parallel. And it's absolutely not the bottleneck of the evaluation. So here I'm playing with increasing the grid size, and I'm comparing the best implementation for the solution method for the CPU, which I believe is not so far from the maximum that we can achieve on this machine, with the argument I explained before, with the GPU. So the problem is my GPU is quite slow because it doesn't deal with 32 bits double natively, so it has to emulate it. So it's basically 6 times slower than it would be at its normal speed. But well, so you have this. So it's a bit surprising to see that the time it takes to process 10 times more data is not 10 times less. It's actually there's some speed up, and the fact that the GPU is faster than the CPU, actually I would have expected it to be faster, because you see on this graph that almost for the 2 operations, the GPU is 2 times faster. So if I can implement the algorithm on the GPU, then it should be, without retrieving the data, it should be 2 times faster. It's not exactly what happened. Okay, so I have insisted a bit on this results, because I think it's important. I mean, it's meaningless to say that the algorithm took 1 minute or half a second if you have no metric to measure it. So I think now the metric is memory bandwidth. It's at least for personal computer. Then there is one thing, there are big gains of doing vector computation in one computer. It's actually, whether you do it on the GPU or on the CPU, it's still vectorized operations. And that is. And this is implemented in a very generic term, so you can apply it to any model that is of the FG class. And you write the mod file and you try it. And this software that is in development, it's really free software. It's under the BSD license. You can download it now. And either you use it as a integrated environment, or you can use it as a compiler, or just to compare, or you don't care, as you wish. But I try to cooperate with at least 2 projects. So one is a Compilation toolbox. I can compile a mod file to the Compilation routine, and the Rex project, which is also a MATLAB-based solver. Okay, so this work will be, it's a 1 year, more or less 1 year work. So we'll see the state in one year. Any question before the coffee?